Hello everyone. I am here to discuss about my seminar topic quantum cryptography. We know that cryptography is the art of science that deals with encrypting and decrypting of messages. That means a message from plain text is converted into ciphertext using encryption or encryption algorithm, and a message from ciphertext is converted even back to plain text by using decryption key or decryption algorithm. So we can go to abstract. This paper deals with introduction to cryptography, some of the cryptographic techniques and introduction of quantum cryptography and differences between traditional and quantum cryptography. We know that traditional cryptography is not as much secure than quantum cryptography. Quantum cryptography uses photons of light to transmit information. Quantum cryptography is the science of exploiting quantum mechanical properties to perform cryptographic tasks. Quantum cryptography is somewhat related to physics, quantum physics. This uses photons to transfer information. The best known example of quantum cryptography is quantum key distribution, which offers an information theoretically secure solution to the key exchange problem. Quantum cryptography is an effort to allow two users of a communication channel to create a body of shared and secret information. That means we know that information is transmitted between a sender and a receiver. So the information passed must be secure. By using quantum cryptography, this provides a more secure solution. The advantage of quantum cryptography over traditional key exchange methods is that the exchange of information can be shown to be secure in a very strong sense. The difference between traditional cryptography and quantum cryptography is that traditional cryptography is not as much as secure than quantum cryptography. Introduction. We have discussed that cryptography is the coding and decoding of secret messages. And to communication takes place between a sender and receiver, and there must be certain protocols and medium to communicate. For transferring a message from sender to receiver, we must ensure that the message must not be viewed by any third party, or it must be as much as secure. Quantum cryptography is the single most successful application of quantum computing or information theory. Quantum cryptography is an application of quantum computing. For the first time in history, we can hope to use the forces of nature to implement perfectly secure crypto systems. Nowadays, quantum cryptography works in practice. Next one, limitations of modern crypto systems. Since public key cryptography involves complex calculations that are relatively slow, they are employed to exchange keys rather than for the encryption of voluminous amounts of data. That is, modern cryptography uses mathematical calculations. For calculating those data, there must require large amount of time. And if there are voluminous amount of data, that means if there are large amount of data, then the process must be complex. That is one of the limitations of modern crypto system. We can look at an example. For example, widely deployed solutions such as the RSA and the Diffie-Hellman key negotiation schemes are typically used to distribute symmetric keys among remote parties. In the RSA and Diffie-Hellman key algorithm, they distribute symmetric keys among remote parties. However, because asymmetric encryption is significantly slower than symmetric encryption, a hybrid approach is preferred by many institutions to take advantage of the speed of a shared key system and the security of a public key system for the initial exchange of the symmetric key. Symmetric encryption is slower than asymmetric encryption. Thus, this approach exploits the speed and performance of a symmetric key system while leveraging the scalability of a public key infrastructure. Quantum cryptography is discovered to overcome the limitations of modern crypto systems. So here it says that quantum cryptography increases the speed and performance of a symmetric key system. Next, we can go into detail about quantum cryptography. Rather than depending on the complexity of factoring large numbers, quantum cryptography is based on the fundamental and unexchanging principles of quantum mechanics. We have discussed that traditional cryptography involves factoring large numbers and involves mathematical problems, but quantum cryptography is based on the quantum mechanics. In fact, quantum cryptography rests on two pillars of 20th century quantum mechanics, that is, the Heisenberg uncertainty principle and the principle of photon polarization. Photons are units of light. Small units of light are called photons. According to the Heisenberg uncertainty principle, it is not possible to measure the quantum state of any system without disturbing that system. Thus, the polarization of a photon or light particle can only be known at the point when it is measured. This principle plays a critical role in thwarting the attempts of eavesdroppers in a crypto system based on quantum cryptography. In this, it says that when using photon polarization, it must affect the system. So it is that this plays a critical role in thwarting the attempts of eavesdroppers in a crypto system based on quantum cryptography. Secondly, the photon polarization principle describes how light photons can be oriented or polarized in specific directions. The photon polarization describes how light photons can be oriented. This means how light particles are transmitted or polarized in specific directions. There are certain directions for the flowing of photons. Moreover, a photon filter with the correct polarization can only detect a polarized photon, or else the photon will be destroyed. That is, a photon filter with the correct polarization can only detect a message. Otherwise, the photon will be destroyed. It is this one-wayness of photons along with the Heisenberg uncertainty principle that make quantum cryptography an attractive option for ensuring the privacy of data and defeating eavesdroppers. That means, in the quantum cryptography, the two advantages involved are the Heisenberg uncertainty principle and the principle of photon polarization. By these two advantages makes quantum cryptography the best. These two processes makes quantum cryptography very more secure, and it helps to defeat from eavesdroppers. Eavesdroppers means a person that involves in secret conversation or who interacts in secret information sharing. A quantum key distribution example. We can look at an example. This example includes a sender Alice, a receiver Bob, and a malicious eavesdropper Eve. Alice begins by sending a message to Bob using a photon gun to send a stream of photons randomly chosen in one of four polarizations that correspond to vertical, horizontal, or diagonal in opposing directions. This example includes a sender. We know that for passing an information there must be a sender and receiver. Here the sender is Alice and the receiver is Bob, and the third party involved in this is Eve. He is a malicious eavesdropper. Here Alice sends a message to Bob using a photon gun to send a stream of photons randomly chosen in one of four polarizations. For each individual photon, Bob will randomly choose a filter and use a photon receiver to count and measure the polarization, which is either rectilinear or diagonal, and keep a log of the results based on which measurements were correct. While a portion of the stream of photons will degenerate over the distance of the link, only a predetermined portion is required to build a key sequence for a one-time part. We can look at the diagram explaining this. Here Alice is the sender and Bob is the receiver, and in the middle of them there is a eavesdropper, malicious eavesdropper, whose name is Eve. The Alice sends a plain text and Bob is the receiver. There must be a public channel or quantum channel, either by telephone or internet the message is passed, or by optical fiber or free space. The plain text is encrypted using encryption algorithm as mentioned in this figure, and it is decrypted using decryption algorithm. I hope you all understand this figure. Next, quantum key distribution. Here Alice sends the messages to Bob. We can see that photons of lights are used and polarizers are there, either horizontal or vertical or diagonal. Alice bit sequence are shown in the figure, and in this figure we can see that photons may be in any directions. Some may be straight, some may be in parallel directions. Here the keys and the Bob's results are given. This is a figure depicting quantum key distribution. Quantum key distribution is a secure communication method for exchanging encryption keys only known between shared parties. The communication method uses properties found in quantum physics to exchange cryptographic keys in such a way that is provable and guarantees security. Quantum key distribution is a security medium, or it is a secure communication method for exchanging encryption keys only known between shared parties only. That means it is very secure. The communication method uses properties found in quantum physics. That is, quantum key distribution involves or uses the properties involved in quantum physics to exchange cryptographic keys in such a way that is provable and guarantees security. It uses quantum physics to provide security or guarantee security. Quantum key distribution enables two parties to produce and share a key that is then used to encrypt and decrypt messages. Quantum key distribution enables the senders and receivers to produce or share a key that is used to encrypt and decrypt messages. We have studied in earlier chapters that a key is needed and the key is known to encrypt and a key is used to decrypt messages. Specifically, quantum key distribution is the method of distributing the key, not the key itself or the messages it can enable users to send. Quantum key distribution works on a scale much different from conventional key distribution in that quantum key distribution uses a quantum system that relies on basic and fundamental laws of nature to protect the data rather than relying on mathematics. Traditional cryptosystems or traditional cryptography uses mathematical problems or includes mathematics to calculate information, calculates the data. So if there are large amount of data, that must be that must be not secure or that is difficult to calculate. So quantum key distribution uses quantum system that relies on basic and fundamental laws of nature to protect the data rather than relying on mathematics. As an example, the no cloning theorem states that it is impossible to create identical copies of an unknown quantum state, which prevents attackers from simply copying the data in the same manner that they can copy network traffic today. Additionally, if an attacker disturbs or looks at the system will change in such a way that the intended parties involved will know. That is, it is mentioned that if an attacker disturbs or looks at the system will change in such a way that the system know that it must be more secure. This is a process that is not vulnerable to increased processing power. How does quantum key distribution work? Quantum key distribution works by transmitting many light particles or photons over fiber optic cables between parties. Quantum key distribution involves quantum physics that we have said earlier. And in this, the units of transmission are light particles or photons. The medium of transmission is fiber optic cables. Each photon has a random quantum state and collectively the photons sent make up a stream of ones and zeros. The photons are in a bit of ones and zeros. This stream of quantum states that make up ones and zeros are called qubits. This stream of quantum sets that makes ones and zeros are called qubits. The equivalent of bits in a binary system, that is the binary numbers 0 and 1, that is called qubits. When a photon reaches its receiving end, it will travel through a beam splitter which forces the photon to randomly take one path or another into a photon collector. The receiver will then respond to the original sender with data regarding the sequence of the photons sent, and the sender will then compare that with the emitter that would have sent each photon. That sender sends a photon to receiver and the receiver will ensure that the photon is correct. Photons in the wrong beam collector are discarded and what's left is a specific sequence of bits. If the photons are in wrong beam, then it is discarded. This bit sequence can then be used as a key to encrypt data. Any errors and data leakage are removed during a phase of error correction and other post-processing steps. Delayed privacy amplification is another post-processing step that removes any information an eavesdropper might have gained about the final secret key. Next, there are certain quantum key distribution attributes that are confidentiality of keys. Confidentiality means we have a key to transfer information or to know the information. That means the key must be confidential and only the two senders and receivers must be know the key. Authentication. Sufficiently rapid key delivery. To prevent more traffic, there must be rapid key delivery. Robustness. The performance of the key must be robust. That means the key must provide secure information. Resistance to traffic analysis. The key used must be secure and it does not involve traffic analysis. That means there must be only limited data If there are voluminous data, then it is difficult, and there comes traffic analysis. Conclusion: quantum cryptography is a major achievement in security engineering. As it gets implemented, it will allow perfectly secure bank transactions, secret discussions for government officials, and well-guarded trade secrets for industry. Quantum cryptography is a major achievement in security engineering. In security engineering, quantum cryptography plays a vital role, and it provides it helps to in secure bank transactions, secret discussions for government officials, etc. I hope you all understand my video. Thank you.